Good evening and welcome. Good, I'm glad. Uh, Welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik, and really glad to have a lot of mostly new faces, at least for me, here for our Friday night program. Um, just quickly, by show of hands, who is sort of new here or hasn't been here since your fourth grade field trip? All right, practically everyone. All right, excellent, excellent. All right, the next question is, who here is a member? All right, basically the other half or the other portion. The people that raise their hands second actually have a valuable piece of information, and that is the value of a Copernic membership. We are a nonprofit, and so we do offer memberships again to our facility here. But we belong to what's called the ASTC, Association of Science and Technology Centers, and it's a consortium of over 380 other science centers that honor each other's membership. So if you like this kind of place, a Kopernik membership is actually very valuable and very cost effective compared to what you might do if you're just constantly going to these places. But like you could go to Roberson Museum, you could go to the Ithaca Science Center, the Museum of Science and Technology up in Syracuse, the Franklin Institute down in Philly, or the Intrepid down in New York City, all for free. So if that has some appeal for you, you can go to our website and sign up. But again, you also get into every one of our Friday night programs here for free. I'm just going to switch over to, okay, here we are. So last year we celebrated our 50th anniversary of being a public observatory and STEM education facility here in the Southern Tier. First and foremost, we are an observatory, but we are, as I like to say, more than 3 telescopes on the top of a hill. We do a lot of school outreach. Now that the school season has started up, schools will be coming up here. We'll be taking our resources into schools to augment their science and engineering curriculum. During the summer, we have a very extensive summer camp program. Last year, this past summer was our 33rd year of offering week-long STEM summer camps for kids as young as entering 2nd grade through high school. And everything we do is always on our website, so you can always find out about what's going on. So tonight's program is on the fall skies. Tomorrow is actually one of our programs called Kopernik Kids, and this is for kids that are between 3 and 6 years old. We're just starting to get them to start to be curious about the world and how and sort of through their eyes, through a 3 to 6 year old's eyes, how does the world work, and get them to explore a little bit. You can find out about more what we're doing in our Kopernik constellations, which is our sort of quarterly newsletter. But one of the things I really love are these Friday night programs. It's an opportunity for us to really expand our knowledge. Not everything we'll talk about will always be about astronomy. In fact, you can go over here to our classes and programs, go to public programs, and you see what's coming up. So again, tonight happens to be about astronomy. But next week is solving the mystery of Easter Island. How did those Moas get to where they were? We've got other, in November we'll have the National Weather Service come up and do a summer review and a winter preview. So it's not always about astronomy, but we, of course, at the end of every program, if it's clear or even partially clear, we'll invite you out to look through our scopes, at the night sky. And tonight, Saturn for sure will be up, and later on, the moon will be up as well. We'll try to have one of our scopes set up so that you can actually take your cell phone and get a pretty neat picture, a nice close-up picture of the moon that you can take home with you on your cell phone. But again, these Friday night programs are really what I really enjoy a lot. And back in 2020, we had to stop doing it because of COVID. We couldn't bring people into a large room. So I said, fine, we'll just wait a couple of weeks until this COVID thing blows over, and didn't exactly play out that way. So we thought after about a month, they said, look, we've got all these speakers lined up. Why don't we have them just zoom into our facility here? We then turn it back around and put it out on our YouTube channel. And so our YouTube channel now has almost 14,000 subscribers. So any of our public programs you can find actually recorded here. So you could go back weeks or months or even years and look at previous previous programs. And as you can see, not all of them were always about astronomy. Here is talking about what's causing butterfly declines. We've had a talk about the Galapagos Islands. So we've had high school teams, high school robotic teams in here talking about what they do. But also, anytime there's any sort of a astronomical event, a lunar eclipse, meteor showers, aurora borealis, we will actually do an observing session with that. In fact, actually, Jenny Cartie, who's our speaker this evening, back in March, there was a lunar eclipse, if any of you remember that. And, of course, we're going to see the ad. So let's go here. So this is just a time lapse of what was ultimately about a 4-hour event. And you start to see the penumbra start to cover up the. Let's see, where's the. So actually, she had to go and change the exposure so that we could actually start to see the blood moon. Now, a lunar eclipse, this blood moon happens every lunar eclipse, and clearly it was not the end of the Earth, as is often predicted. But what's happening there is when the Earth covers up the sun, there is sunlight that's actually refracting through our atmosphere, and it's that long wavelength, the red light, that actually comes through. And that's why the moon always looks red when it's in an eclipse. And then finally, we came out of the eclipse. So these are the kinds of things that we can do here. Again, among our 14,000 subscribers are literally people around the world, and often there's a woman, Lindsay, who lives in Adelaide, Australia, will often be watching this live. So for her, she's actually just finishing up breakfast and putting away her dishes and watching our program. So anyway, we're very fortunate to have on staff Jenny Cartie, who actually started out as a high school intern, ultimately got a degree in physics and then a master's degree, and now works for us as our technology manager, but our lifetime astronomer. And so I'm going to bomb out of this and go into Jenny's. All right, so Jenny, off to you.
I think it should be, but if you want to double check, it sounds like it is. What's that? Oh, I think the lights are okay as is, yeah. All right, let me just bring this full screen here. Yeah, all right, so hello everyone, my name's Jenny, and I'm going to be leading you towards this little intro of astronomy, giving you some basic tools and concepts to help you map out and understand the sky, and then of course bring that to what's out in the sky right now this season with fall skies. So let's get started. With our skies program, we always start with our ABCs. So that's going to be the first step, is the ABCs of stargazing. And that's the concept, the little intro to astronomy tonight. And then we go on to what can we see in the sky, and wrap up with some observing tools you can use that you can have access to. All right, ABCs of stargazing. And the background, at least the major background you'll see throughout the show tonight, I won't talk about it too much yet, but it is teasing something that could happen at the end of this month. We're really hoping it does. All right, so A. So these are your ABCs, and they, at the scientific and astronomical scale, what scientists use these for, they are kind of, some of them more abstract concepts, and they are complex, but we're going to narrow them down a little bit. this is angular size and distance. So how we are measuring the distances between objects and also how big an object actually is. All right, I should try the clicker too. So this is your handy trick. Why isn't that going away? There we go. This is your handy trick that you can use. It's literally your hand. And you can measure the sky using just your hand. And we can practice this right now. You can even start measuring angular distances in the room if you want. But using different hand gestures, you get different angular measurements. And we can use these in the sky. So raising up your pinky, the width of your pinky at arm's length. That's an important thing. Getting feedback. So at arm's length, we have 1 degree for your pinky in width. Fun fact, your pinky nail, the width of your pinky nail is about the size of the moon, which is fascinating, right? Like you reach your hand out, the size of the moon is about the size of your pinky nail. We picture the moon in our mind as this big object. Well, that's because it's one of the biggest objects in the sky at all that we can easily spot. It's about the same size as the sun, but it's still pretty small. And there is that optical illusion too, when it's near something that we know, like a hillside or a tree, it looks big when it's near the horizon. But as it climbs up in the sky, it looks smaller, but it's an optical illusion. It's not changing in size at all over the course of the night, which is really fascinating too. Just our brain playing a trick on us. So 3 fingers at arm's length, that's 5 degrees across. And then you make a fist at arm's length, that's 10 degrees across. And I always call this, because of my family, that's the hook'em horns. So you do that at 15 degrees across. So with that, you can practice these. Even if you wanted to take a picture of this slide right now, feel free. Because you can practice these on bright constellations like the Big Dipper. Now, this time of year, the Big Dipper is pretty close to the horizon at this time of night. So you'll have to move away from the building to see it at all. But it's a good example because it's made up of really bright stars, easy to find and easy to practice this method with. So that's your angular distance. Next we have B for brightness. And in the field of astronomy, we call this magnitude. And there's different concepts of magnitude and how bright an object can be. There's apparent magnitude, which is what we see from the ground here on Earth. And then there's also an absolute magnitude measurement, an absolute luminosity that an object has inherently. And that's important because if you have 2 very big bright stars of the same type, same size, they're burning the same composition, we'll just call them bright blue stars. But you have them at different distances, just like a light here that you'd experience on Earth, a flashlight at different distances is going to change in brightness. That's the same thing with our stars. So stars also have an inherent absolute brightness, but for amateur astronomy, for just visual astronomy, we focus on the apparent because we're looking up in the sky and observing. So here's a number line, and this is how magnitude or brightness is measured. And you're going to notice something immediate. It's not intuitive. And we have our negative numbers on the left side, positive here, but what's all the way on the left side? The sun. And the sun is the brightest apparent object in our sky. So it's all the way out towards -30. And that's exceptionally bright. On our number line, it's a negative number there. And we go down the line, we get to a full moon. Okay, definitely not as bright as the sun, but as you'll see tonight, as the moon rises above the horizon in the tree line, the moon's really bright. A full moon is super bright. So that's our full moon on the chart. But also, I will say, we'll see this in the slide coming up. Sun, you don't want to observe by any means directly. The moon's totally safe. It might make you feel like you're going blind on a dark night, but it's safe. Then we have Jupiter, one of the brighter planets. Jupiter and Venus are two very bright planets. And they fall, Jupiter here, it does change. The planets do change in magnitude as we orbit and they orbit. But this is at around a -3 on average. And then our 0 point, our 0 marker, you'd think like, okay, what would a good 0 marker be? Well, it's the star Vega in this case that I have marked here. It's a pretty bright star. You'll see Vega tonight during the star tour. It's also the star that we hear the signal from in Contact, if you've seen that movie. It's a good movie, good book too. Recommend it. But we haven't received that in real life. Then we have around a 3 magnitude for Andromeda Galaxy. That means that you can see it, because the faintest objects that we can see with just our eyes in very dark skies is around a 6. After that, we can't really see stuff with just our eyes. With binoculars, you see more. It goes up. With telescopes, you see more. But our eyes are limited to about a 6. You can see the Andromeda Galaxy tonight. With the moon coming up, we'll have to see. But it is visible this time of year. It's a good object. And then out here, we have something like the Ring Nebula, a little faint planetary nebula. And that also is in the same constellation Vega's in. And that's out towards A9. And it keeps going. And eventually you get so dim that the kind of light we're seeing isn't visible light. It's infrared light. That's what the James Webb Space Telescope sees. But we can go super faint out there on this chart. Now, quick explanation as to why the number line is the way it is. This was originally, astronomy is a very old science. It grew with the scientific method, and from fairly early on, humans were looking up in the sky and trying to make measurements, figuring things out. And this started as a classification system for stellar brightness. So if you're classifying something and ranking them, you count the brightest thing as a class 1, and then a class 2, and then a class 3. And that legacy just kind of carried on, and eventually mathematics were applied to it as well. But that's how this classification system played out for brightness. All right, C is for coordinates. And we talked about measuring angular distance with your hand. That starts to apply here. At the very base level, we take that concept of measuring angles across the sky and apply it to an organized coordinate system that we call the altitude azimuth system. And that's what it looks like. So for our altitude azimuth coordinates, this is you tonight. And you're looking up in the sky, and you can just do basic measurements and just like point to something, point to the horizon, and then kind of count up in the sky. You can totally do that. But if you're doing it in an organized way using the true alt-az coordinate system, on the horizontal, on the ground level, where your horizon lives, you mark out, this is your azimuth. You mark out on north, that's your 0 degrees, east is 90, south is 180, and west is 270. And then your altitude is measured from 0 to 90 degrees. So something like the North Star, which we can see tonight, the azimuth, it's the North Star, it's at 0, and your altitude is your latitude. So does anyone know our latitude here, roughly? It's in that range, yeah. I think ours here at Kopernik is 42. And if you measure from that horizon to the North Star using that method tonight, finding the true horizon's tricky up here because we have trees around. But if you estimate, you should count around 40 to 50 degrees in that range. So worth trying out. And then we just have some random star in the sky, and you could measure from the horizon, you get the altitude to 50 degrees and measure your compass directions to get your 150 degrees, and that's your azimuth. So this is really helpful for momentary glances at the sky and building out a coordinate system with respect to you on the ground. So this is your field of view. Okay? We have another one. And this is more useful for giving objects to the best of our abilities, because things do move. Like planets move, comets move, especially things in our solar system, and even over time the stars will move. Not significant over a human lifetime, but still. This equatorial system, though, does the best job at giving objects specific coordinates in the sky. So now we're mapping the coordinates out to the star field and locking that coordinate in place so that it moves with the stars and it moves with the sun. So let's take a look at how the equatorial system is pieced together. So I even have some globes up front. That's kind of what we're going to start to see here pieced together. We have an Earth globe. I'm sure we're all familiar, right? This is the planet. And then we have our star field globe. Okay, so these are all the constellations we can observe. And this we imagine as a sphere wrapped around the Earth. This is actually how astronomy started. This was a what they thought the universe how it worked. It was a shell around the Earth with the stars mapped into it. We can still use that model today. It still works, especially for coordinate planes. All right, and then you have it all together. I'll come down with this one. It's kind of what's pictured there. We're going to build this on the screen. We have the Earth in the center, and then that shell around the Earth mapping out the stars. And this is where the coordinates of equatorial live. Is in that shell. So let's piece it together on the screen. Earth at the center, and we have our star field all around it. Hang on. It went, this is skipping around. Oh, wow, it's really it skipped all the way to the end. Okay, this has a mind of its own. I think one of the buttons got locked out, which means I'm going to just take out the battery. So it doesn't skip through my slides. Okay, let's try again. All right, we'll just use the keyboard. So there's our shell and the Earth. We map out, we take Earth's equator, and we project it out into that sphere of stars. That's what we call the celestial equator. And then, just like our own coordinates, latitude and longitude on our globe, we can map out latitude lines on this sphere. We have the sun, the context of the sun. What does it do in this sphere over time? Where is it positioned with respect to Earth, our equator, and so on? This is also showing you how the seasons work. It's another way to think about how our seasons work, driven by Earth's tilt as we go around the sun. So this is we've mapped out now our right ascension. These lines here are your declination in this grid. As you see, it's getting more and more complicated as we go through. And after the program, if anyone wants to see this up close, this 3D model does a really good job. So you see the equinoxes here, the spring, that's the fall back there. So going from spring to summer, to fall, to winter. And those are for the northern hemisphere. Winter and summer, everything gets flipped around for the southern hemisphere. Okay, so, that was the last slide. So we have these two, just like we had altitude and azimuth, we have similarly right ascension and we have declination to map out our grid. And this lines up with the constellations in the background. And we're going to look at this in Stellarium to see, okay, that's all well and good. That's how it's built, but how do we use it practically? And this is your first, if you're new to our SKIES program and astronomy, this is going to be a good look at some software that you can get. I'll just show you the web page where you can download it or access the web version. You can also download it on your smartphone or tablet. And this is for any platform, pretty much. The downloadable version for desktop PCs and laptops is more advanced. That's the one I'm going to work with tonight. The web-based version is a little simpler to work with as an introductory model. But we'll jump into this one here. So I'm going to also turn the atmosphere back on, and I'm going to return us to current time. So as a simple sky we have here, with just some labeled stars and planets. It looks like it's mapping out some meteor showers as well. It's just a simulated view of the night sky for a given location. So we have it set up for our observatory here, but you can set it up anywhere on Earth or even beyond. If you wanted to see what the skies look like on Mars, you can do that. This is really powerful for seeing what's out in the sky. This all just shows you how strong our model of the sky and the objects out there, how good it is. This can scale up out to thousands of years into the future. So it's a time machine through the sky, and it's a teleporter of the sky too, so you can jump around. So we have it set up, if you see in the southwestern sky there, for those that went outside and saw the Milky Way, that's where it was, the compass direction. We have compass directions all the way around. If you've ever been in a planetarium before, that's what this is basically. But this is your at-home planetarium. Instead of looking around, you just click and drag or touch and drag and move the sky around. Really powerful tool. You can turn on constellation lines, labels, artwork for the mythology, and we'll go to that extent just to clean up the sky a little bit. We'll leave the artwork off for now. And you can also map out your grids. So starting with our azimuthal grid, this is your altitude and azimuth. You look around. For altitude, you go from your horizon all the way up to the tippy top of the sky. And this point here is called your zenith. If anything is at the zenith, like Cygnus tonight, it's a pretty bright constellation to pick out. We'll show you on our star tour, but you'll immediately, your neck is going to start hurting when you do that. So that's your altitude and azimuth. Just for fun, I'll show you what they look like overlaid. It's a mess. And I'm going to turn azimuth grid off just so we have equatorial, and you see how it's canted. It's a similar type of grid, but again, we're mapping it out with respect to how the Earth rotates with our equator expanded outwards in this grid. And that means that if we project the polar axis, the north polar axis of the Earth here, if we send that out into space, it should line up with the North Star. And it does, just about. Very nearly. This is the North Star in Ursa Minor here. That's the tippy top of our grid in declination. And you can see the North Star is just about that due north. It kind of circles around this central point here. That was a satellite. Yeah, probably a Starlink. So yeah, it'll track satellites. It'll show you where the ISS is. We'll get to that too. But yeah, it'll track satellites. It'll track comets. The downloadable version, you can really expand out with all sorts of options. So yeah, that's your equatorial grid. And we use, for our tracking telescopes, the equatorial grid works really well because you can synchronize your telescope with an equatorial mount to the rotation of the sky. And that's how all three of our dome telescopes work. With the right motor speed and that combination of a mount that maps out to this grid, you can have the telescope track. So when you observe things tonight and you don't see the object move in the telescope, that's the tracking working. And that really helps us because we can get lots of people through to see that object at once. If you go out to one of the portable scopes outside that's not tracking, you'll see how quick the object moves out of view. And that's the Earth's rotation in action. It's really amazing. All right, we'll hop back in here for now. That. We'll come back to stellarium throughout the talk here, but now we're going to get into the detailed stuff. What can we see in the sky this fall? And I mentioned with our satellites that we can see the International Space Station sometimes, not tonight. But this is the ISS. It's the largest human-made object ever constructed in space. It's the size of a football field. A lot of that space is taken up by the instrumentation and, of course, the solar panels that power the craft. This object is in low Earth orbit, and when it flies overhead, we can spot it. So it orbits just under 250 miles above the Earth, and it's doing that orbit once every 90 minutes at that speed of 17,500 miles per hour. So this thing is booking it, and at that speed, you could travel from New York to Los Angeles in less than 9 minutes. So moving super fast, and that means they get this view of the Earth that we can watch in videos for sure, but all astronauts will tell you, seeing it with your own eyes, and just, it was especially profound during the pandemic too. Some of their thoughts on knowing what was going on down there. They were safe up there on board the space station, but it was really just this profound moment for them. And it always is, looking back at the Earth. That was the same thing during the Apollo era, seeing that moon rise, Earth rise above the moon. Really incredible stuff. Now, you can look up the ISS flyovers. You can also track it in stellarium. That's not the best way to do it. It will simulate that flyover, but it's better to have exact directions, times. A nice table like this really helps out. So here's some upcoming flyovers. If you wake up early, you can catch them. Don't worry, this isn't always the case. If you want to wait until you see them in the evening, it doesn't take long to see them in the evening rather than the early morning. But we have some good flyover on October 13th, 15th, and 16th. Where's a good place to look? Well, there's apps. You can download some apps for ISS flyovers. There's also this one that we use sometimes called Heavens Above, which is a satellite tracker. I'm just going to show you that briefly. So on Heavens Above, you go to map out your location. I'll just use the browser settings for it. The ads have gotten worse on this website over time, Drew. We'll update. And we'll go to ISS. And there are the 3 flyovers I mapped out in that table. And you can skip ahead into the future to see other ones, lots of early morning ones coming up. So again, if you wake up early, that's a good time, but there's some evening ones too. That's starting, looks like, almost mid-November, November 10th. So the ISS, when it flies over, is this, it's not, you don't see any detail, of course. That's a long ways up, but it is big enough that it's reflecting a whole bunch of sunlight back down at us here on Earth, and it looks like this bright star moving across the sky. All right, we'll exit out of that one and back into here. And yeah, we will go to this website too. I do have this little thing that plays on this slide to give you an example of what the ISS looks like in the sky, just like that. Big bright star moving across the sky at a constant rate. And no blinking lights, yes. That's a big one too, because it's just sunlight reflecting. Sometimes you do get satellites that are more like space junk now, and they tumble. And when they tumble, they like usually blink at a regular rate. But it's still just reflected sunlight. So this is a website called Who Is in Space. It's exactly what you'd think. It tells you how many people are in space right now. It says there's 10 people in space. So you can scroll through. It'll tell you what mission they launched aboard to a space station. So this is SpaceX Crew 11. And see, there is the Soyuz MS-27 mission. And finally, we have the other space station as well, the Chinese space station, Tiangong. And there's 3 astronauts aboard that one. So that is a total of 10 people in space. There are, yes. The NASA and led one, it's a huge collaboration between NASA, ESA, CSA, JAXA. CSA's Canada, ESA's Europe, JAXA's Japanese, and then the Soyuz components are the Russian modules. So it really is this massive international effort. And that's why you see the astronauts that flew aboard. So Soyuz flies with cosmonauts from Russia and 1 American astronaut. And then we're getting some weird feedback. And then the NASA missions that fly with the SpaceX system, those ones are American astronauts, and then 1 cosmonaut, and then usually an astronaut from another country as well. In this case, from JAXA, from Japan. Oh yeah, so that's collective time. So a lot of these astronauts keep going, will return to the space station or another mission, maybe in the future, like Artemis. So this is their collective time in space, not their current duration on the space station. Yeah. Yeah, yep, because the Boeing issues that they weren't necessarily confident with bringing that spacecraft back with astronauts on board. Yeah, there were some astronauts. Suni Williams, I think is her name. she was up there for longer than she expected, because it was really just supposed to be a test mission to the ISS. All right, so exit out of that one. And now we'll talk solar system. Lots of fun stuff happening in the solar system this fall. So I start with the sun, mostly to tell you not to look at the sun. We can up here. We do solar observing at Kopernik. And there is stuff to see on the sun, especially with different types of telescopes. We can see sunspots on the sun, these dark patches on the sun. These are basically magnetic storms happening on the surface. But with different filters, with different equipment, you can bring out the flares and the prominences on the sun. So there is things to see at an observatory like this. We always say, don't try this at home. Don't stare at the sun with your eyes, not binoculars. If you have eclipse glasses that are in good condition from 2024, you can look at the sun with those. That's the only, but they have to be in good condition. The lenses can't be bent or have any pinholes in them. They're safe to use on a non-eclipse day, but just make sure they're in good shape. And sometimes, if there's a big enough sunspot, that happened a few times over the last year, you can see them with just the glasses alone, which is pretty cool. So otherwise, don't look at the sun. But there are things that happen with the sun that are pretty interesting and cause some interesting things in our skies. So solar maximum, they believe it peaked, and now it peaked back in July, and now it's plateauing, and it's even possibly starting to come down. This happens on an 11-year cycle. The sun increases in activity and then decreases. Normal cycle, we're on solar cycle 25. Not just coincidence that it maps out to the year that it's happening in. They started measuring sunspots. That's the true measure of solar activity. How many sunspots are on the sun? You're just counting, and it goes up as the activity increases. So they started doing that in 1700s. And if you count out towards 2025, eventually you'll get to 25 solar cycles. But when that activity increases, we get some pretty amazing things that can happen in the sky. There it goes. Like the northern lights. And even though we may be waning in activity, this was a storm from, I think this is the one from August of last year. We also had one in October of last year. Even though the solar maximum might starting to be going down, there's still going to be a lot of sunspots, and those sunspots produce solar storms. When the storms are big enough and targeted towards Earth, the northern lights activity increases. This is a direct effect of that solar radiation hitting us. And we see it as this beautiful display of color in the sky. So it can really dazzle, and you'll hear reports, I'm sure over the last year, you've heard all sorts of news reports and things. Maybe you can see the northern lights tonight. A lot of the time it's like, I didn't see them, but there are some nights where it's a very strong showing, and you can get them even to the point, now this is camera view, but with your eye, I could totally see the colors. I could see the greens, I could see the pinks. They were duller than what the camera is picking up here. But the shape of it was there. It was just amazing. And the October storm was even better than this one. October last year. So if you want to track, a good website that does incredible tracking for these events is called spaceweather.com. And this site will show you a daily view of the sun, how many sunspots are across it. It'll give you, even beyond the sun, what else is happening in the sky. It'll give you some current events, some interesting objects to observe. But if you scroll down on the side, you get this probability map. of where aurora can be seen right now. And it's all up further north, so we wouldn't be seeing them tonight. If you click on more data, it gives you the chart of activity, and it's measured, the geomagnetic storms are measured on this scale. So there's two things going on there. There's this thing called a KP index, and that also aligns to geomagnetic storms, which are classified kind of like you'd think a tornado or a hurricane. They have different classifications. So a KP5 is a G1 class storm. KP6 is G2, KP7, G3, KP8 and 9 is G4, and then outwards is G5. For our area, if you look at this chart and start seeing oranges, that is a sign that we might be able to see them from our area. Out here, if you go up north to the Great Lakes, G2, you can usually see them there. But G3 is what we'd like to see here, and even better, we'd take a G4, because that's when they're way overhead and nice and bright for our area, like the storm we saw on the screen. So good tool there. There's still a chance over the next even couple of years that we might get some more big storms. Okay. Now, still in the solar system, the moon. We love the moon. We like to observe the moon, but it does get in our way sometimes. We wish we could turn it off because while it's beautiful to observe, and for so many, when you get your first telescope, this is what you look at. It changes, it's a dynamic, right? We see different phases of the moon on that lunar cycle of almost 30 days. But it is super bright. And as it rises tonight, if you saw the Milky Way earlier, you won't be seeing much of the Milky Way from this point on as the moon rises, just because it starts to drown out the sky. So how to observe? Well, you can, of course, look with your unaided eye. You can use binoculars, telescopes, and cameras. So the reason I put that in there is because it is very bright, like I said earlier, but it's totally safe to observe no matter what. You're not ever going to be putting so much light into your eye that you're damaging it, even though it might feel like it on a dark night when you look through a telescope and this light blasts your one eye. It can be pretty concerning at first, but your eyes will adapt. All right, planets. Summer was very quiet for planets. If you stayed up late, you could see Saturn, but that was pretty much it for evening objects, evening planets. But now as we head into fall, Saturn's already out right now, easy to spot, easy to observe, and that's been the case over the last month at least for evening hours. And now Jupiter is starting to come up. Just barely. It's like right around midnight, it'd be high enough here at Kopernik to start observing. But as we head into the later fall months, that's just going to get earlier and earlier. So it'll be more around as we head into late November, probably something like 10 p.m. where you can start observing it. So it's going to be best in the winter at an evening hour, but Jupiter is a fall object too. Saturn, though, lots of interesting things happening with Saturn this fall. We had a whole talk about that a couple of weeks ago, focusing on the opposition of Saturn. That's our close approach to Saturn, where Saturn's on the opposite side of the sky from the sun. And that means we're getting as close as we can to it in our orbit around the sun. And that comes with things like the rings brightening up. There's some interesting effects that happen there where the rings get super bright. We might see some of that tonight as well. But other things happening we focused on during that talk. This is actually showing you the effect of that, this little animation. But you see this little spot. It's not a bug in the telescope, I promise. It's a shadow from one of Saturn's moons, specifically Titan. And now the next time we will see that event happen for Titan, a Titan transit, won't be until 2038. So it happened several times over this year, but I believe October 6th was the last time it happened until 2038. September 20th is this recording here from our 6-inch telescope. And there's a similar transit event happening in this picture of Jupiter from, I think this was taken in 2020, where you can see the moon Io there, and it's casting a shadow onto Jupiter. And it's these shadows, that is exactly a solar eclipse. It's just like the solar eclipses we have here on Earth. Now you can't stand on these planets, but it's the same effect. Those moons are blocking out the sun from that perspective on Saturn and Jupiter. Now with Saturn, you may notice something weird about it. The rings specifically. It's kind of a unique view, kind of novel to observe Saturn like this, where it almost looks like there's a needle poking through it rather than structured rings. So here are, I went back through all my photos of Saturn over the years, going way, way back, and this is to show you how Saturn has changed over those years. I don't have an exact date for this. The metadata says it was 2012. I don't trust that based on how the rings are positioned in this image, but I'm guessing around 2010. And then going to 2013, 2015, you can see my skills improved a little bit here over time. Blurry, blurry, blurry mess, then we start to get clearer. But even still, you can kind of see how the rings are positioned during this time. And here's 2020, and then now going to 24. These are almost exactly a year apart, these two images. And you're noticing that the rings are becoming more and more edge-on as we go through this cycle. And what I find so exciting and novel about this is that this is really the first time I've ever seen Saturn this way. Like, I was too young at the time before this point when the rings were edge-on like that. Back in 2008 and 2009, I wasn't looking through a telescope at the time. I didn't know what Saturn looked like then. Now I get to see this novel view of Saturn that doesn't last long, but really interesting to observe, where the rings are edge-on. And why is this happening? Well, Earth goes through seasons, kind of like what we talked about earlier, right? Because the Earth is tilted as it goes through its orbit around the sun, that tilt drives different angles of sunlight hitting the Earth in different parts of the Earth. So for us here at 42 degrees latitude in the northern hemisphere, we are here in the autumnal equinox, or sorry, in autumn, past the autumnal equinox. And this is when we're getting, we're starting to move towards less direct light. As we go to the winter solstice, this is the longest, this is with the longest night of the year, and we're getting very indirect sunlight, meaning we get cooler and colder temperatures as we go through. And then in the summer, it's the opposite effect. You get very direct sunlight at that angle for our latitude. But here with Saturn, we have the same thing going on. Saturn goes through seasons, but notice the dates. This is showing you how long Saturn takes to orbit the sun. We just got into the autumnal equinox here in 2025 with Saturn. This is showing you the view from Earth. From our perspective, what does Saturn look like? We have nearly edge-on rings. 2032 is winter solstice. We'll be looking at the southern hemisphere of Saturn at that point, in the bottom side of the rings. Then spring equinox in 2039, back to edge-on. And then summer solstice in 2046, northern hemisphere, top of the rings. So that's why this change in the rings is happening, but it takes a long time for it to happen. November 23rd, it will be when the rings go nearly completely edge on, and they likely will appear to almost completely disappear. So we'll have a nearly ringless Saturn at that point. So that'll be pretty neat to see. Obviously, we want to see Saturn with its rings, but we'll get back to that really quickly. This is kind of novel. All right, very quickly going to the planets in Stellarium. It's not the only, those two, Jupiter and Saturn, aren't the only ones out. You can do searches, by the way. I should show you that. You can just hit the finder and put in Saturn, hit enter, and it'll take you right to it. And also with Stellarium, you can zoom in like a telescope and see those nearly edge-on rings. If we skip ahead through time, so you see how the rings go more and more edge-on and then almost completely disappear here on the 23rd. They truly disappeared back in March, but the Saturn was too close to the sun at that point. It wasn't really observable. So this is the best we get here, is nearly edge-on. All right, let's go back to current time with this little hourglass. Snap it back into view. You can see some other little lunar transits here. This one's from Rhea, casting much smaller, though, than Titan. Titan's the biggest moon of Saturn, and the shadow was really big compared to that little dot that would be there. All right, we'll jump to Jupiter. And you see it's below the horizon. We're not seeing anything here. But if we skip through time, there it is. And again, we can zoom in really quick. Okay. And if we change let's just skip ahead a whole month. We'll do this in one instant. So if we skip to November, see how much higher Jupiter is in the sky? That means it's rising earlier for us. And again, that we'll see it earlier and earlier as fall goes on. All right. Then meteor showers. What do we got going on for meteor showers? There is a few coming up in the fall. Some of them better than others. Well, specifically one of them. This picture here is from the August meteor shower called the Perseids, which are also really good. One of the better meteor showers. But the Orionid meteor shower has a predicted peak of the night of August 20th going into the 21st. And when we call these Perseid, Orionid, and so on, it's the constellation that the meteors appear to radiate from. We have other talks about comets and meteors too that come up, especially during these meteor shower events. So if you want to learn more, just stay tuned for that. But meteor shower rate is about 10 to 20 per hour. Perseids are more on the best ones, more pushing like 100 per hour. So Orionids aren't as strong. Similarly, the Leonids, not as strong, although the Leonid meteor shower is responsible for something called a meteor storm that happened, I think it was 1966. And there it was like everywhere you looked, from what I understand, it was just meteors every instant, constantly across the sky. Those are rare. The Leonids is known for them historically, but not every year. It's even rare for the Leonids. So most of the time it's weak, but every, maybe several decades you get a storm from the Leonids. Predicted peak is the night of the 16th, November 16th going to the 17th. Now, the Geminids are one even I forget about because it's freezing. It does help to stay up late into the night for these meteor showers, so the constellation's nice and high in the sky. But yeah, as you go later in the night in the wintertime, it just gets colder and colder, especially up on our hill here. So this meteor shower is really good, though. you can get 120 per hour. And they end up being bright, quick meteors. That's going to peak as we head into winter, December 13th to the 14th. Now, we're going to call this segment Jenny Spaces Out, because this is a tangent, and one I hope pans out in some ways. This is all related, though. Meteor showers come from comets orbiting through the solar system. The debris they leave behind is what we run into, and that's what produces meteor showers. Sometimes that debris is denser. That's what would be a meteor storm for, like, the Leonids. Sometimes it's more spread out, so you don't get as many. But comets are responsible for that. Here's Comet Atlas from last year above the science park. This was imaged on a smartphone, by the way, just on a tripod, to be fair, but otherwise no other tools. Night sight on it actually was astrophotography mode on a Google Pixel, and it took up this brilliant shot, really incredible. And that was October 15th. Really solid comet with this massive tail that you could see with your eye. It just stretched across the sky. It was incredible. Yeah, that is you mean the exposure for the camera? Yeah, it takes, I think, astrophotography mode on the Pixel 8 usually pieces it together over the course of a minute or more. Like if you took a picture on an iPhone, I think the max you can go up to is 30 seconds. But both of them do a pretty good job with astrophotography, and it's worth trying out tonight, both with a telescope but also handheld with stars in the sky. You'd be surprised what you can get. Before we get to the Milky Way, I just want to highlight, again, tangent. This comet Lemon we want to pay attention to, because it's already visible to telescopes. It's reasonably bright in telescopes. As we head towards late October, we're going to, it's going to be on close approach to Earth. It's not going to hit Earth, but we're going to get closer and closer to it, and that'll brighten it up. And they predict that it could get to a brightness similar to Comet Atlas that was visible by eye. So be on the lookout for this comet. Here's an image of it here on the screen. It's a very active comet compared to Atlas, in the sense that it has all this particulates. As it gets closer to the sun, these pieces are chunking off of it, kind of creating their own debris trails in addition to the main nucleus of the comet here. Anything else I wanted to mention with this comet? Yeah, we're just going to keep an eye on it as we head into October. It'll be similar to Comet Atlas as well, where it will be just after sunset will be the time to view it and try and catch it. And then just this other small tangent. Remember a few months ago when you heard about that weird interstellar object in the news? And like, ooh, what could it be? Is it a spaceship? Is it an alien? What's coming into our solar system? It's not. It's a comet. But it's an interstellar comet. This won't be visible from Earth with your eye or anything. It's going to be still pretty far away as it comes through. But there are images of it coming from pretty advanced telescopes across the globe. Let me see if I can find a good one here. There's one. So most of the comets we see are comets from our solar system, pretty far out in some cases, with tens of thousands of year orbits sometimes. Others with shorter orbits, like 60 years or something. But this comet is not from our solar system. And in fact, it's likely that this comet is older than the age of our solar system itself. The highest estimate I've seen right now is something like 7 billion years old. So that's pretty incredible. And it's moving so fast that it's not going to get trapped by the sun. It's just going to come in as a little visitor and zoom back out to go find another star. And it just keeps doing that through the Milky Way, being affected by a star's gravity, but it's moving too fast that a star can't capture it. So this is a comet, we'll go up to the top here, comet 3I Atlas, discovered by the same network as the previous comet from last year. The 3I, the I means interstellar. 3 means how many we've discovered. We've only seen 3 of these types of comets. So this is the 3rd discovery of an interstellar object like this, moving between the stars in the Milky Way. All right. Do have to start wrapping up here a little bit. We saw the Milky Way tonight, and it will be a good object for the rest of this month and even into November as well. But as we head towards winter, we start to lose it, at least the brightest parts of it, like the core. So if you want to see the Milky Way, it'll be back in the summer, in the late spring into summer, but this is the time. There's an image of the Milky Way with Comet Atlas, a meteor, and the Milky Way there. Again, taken above the science park. It's not AI. Not that one. No, in fact, none of them are. But yeah, this one was, this may have been an iPhone. Based on, like, an iPhone has this kind of weird artifacting that it does in images, and I'm seeing some of that here. So I think that was on an iPhone. All right, so deep sky objects. I do have a star map that when the program ends, you're welcome to take with you. Oh, let's make sure you will actually be able to grab one, unlike I can right now. There you go. This is handy because it shows you stars. Unlike a star wheel will show you stars, and you can go through all the course of the year. But this is unique to October 2025, and it will also show you planetary positions, because those do change over the course of the year. So this is what we can see in the evening in October. And it has the constellations mapped out, some events happening, and then on the back side, you have all sorts of listings like objects you can see with naked eye, just your eye, with binoculars, and with telescopic objects. And there's all sorts of deep sky objects in here. Deep sky objects are globular clusters, star clusters, open star clusters. They're nebulae like this, the Trifid Nebula, which is good to observe. What else do we have? Oh, and Andromeda, I think I have a picture of too. Oh, there's the Dumbbell Nebula. So Trifid is where stars are being born in space. It's pretty close to the heart of the Milky Way, at least in the sky. And the Dumbbell Nebula is named the same thing, but it's a different type of nebula. This is planetary. A planetary nebula because in a telescope it kind of looks like a planet. It has this orby shape to it. But this is where stars died, and you can see the dying star at the center there. And these types of nebula are looking into the future, 5 billion years, to what will happen with our sun someday. When it dies, it will become a planetary nebula. These are also cataloged with these M numbers, M20, M27, and M31. And it's these catalogs that we use in the field of astronomy. You'll see them listed on the back side here. But the M comes from an astronomer from a couple centuries ago named Charles Messier. And this is his Not Comets catalog, because he got tired of people coming to him and asking, is this a comet? It's not a comet. I don't know what it is. I can't tell you that, but it's not a comet. So they didn't know what these interesting objects were, arguably more interesting than a comet. Think about how many comets are happening in here in the Andromeda galaxy, made up of billions of stars and solar systems. So that's M31. Not their fault. It's the progress of science and astronomy that brought us to this point, where we understand what they are now. We are going to skip that part because we're running out of time. Some observing tools you can use. Stellarium, of course. Feel free to take pictures of these slides as they come up. So stellarium.org is where you want to go to download and access this program. These are other apps that you can download on your phone. Kind of scale, these two are very similar. They're basically aesthetically different, but serve the same purpose. Starwalk and Sky Guide. Sky Safari is where you want to go for the most advanced mobile sky viewing experience. It even has controls You do have to pay a price for it, but it has, if you get a smart telescope someday, you can control the telescope with it. It's really powerful software that runs right on your phone. And your smartphone, in general, the camera on it can take some pretty amazing pictures. Now, okay, to be fair, this was taken with the phone, but hooked up to a telescope. This telescope specifically. But this is the handheld view. So just taking handheld, I kind of had it resting with my hands against the telescope to stabilize it a little more. But this was the lunar eclipse from March of this year. Looking out in the sky from the scope and then into the telescope at maximum eclipse. So there's a lot of versatility with your smartphone. You can hook it up to optics, or you can just use it alone. You'll get some amazing images. And I always like to wrap up this program with clear skies. And we are actually doing that tonight, which is amazing. So yes, clear skies, everyone. And we are a little bit late. Do we want to go through a couple of questions? Okay.
Give me a second here. We make sure that the people on the live stream can also hear your questions. So if you have a question, you want to raise your hand? Okay, over here.
You pointed out one of the Starlink satellites going by.
Yeah.
Have they degraded any of your ability to observe at night so far?
They are annoying, to be honest. Not from a visual astronomy standpoint alone. It's like satellites, even 10 years ago, felt more novel. Like, ooh, there's the ISS going overhead, which is still exciting. Like, lots of education and science happens aboard the ISS. It's an important tool. The Starlinks are just so constant and so overwhelming now that it's just like, there's another satellite, there's another but they do serve a purpose. They're a powerful tool. It's just, this is where I'm getting more into my opinionated stance on the whole subject. You shouldn't be launching from all different companies these satellites. They should be a utility, and they should exist as this constellation of satellites is one thing. But the problem is Starlink's doing it, or SpaceX is doing it with Starlink. The Blue Origin is trying to do it with their own constellation network. And if we have all these competing things happening, the sky's just going to get filled up with junk. And yeah, we're starting to see that. And from a visual and from a data collection experience, it is starting to become a problem.
Sort of to add on to that, many of the images that we take here at Kopernik or any other observatory are often long time. Like they will take a long time base, image. So you might have a 3-hour image, looking at something, and all of a sudden, shing, 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 just comes right through your image, and so you've lost that.
Yeah, they're
pristine.
And you can process them out. Like there are tools now, but we had to develop tools now to counteract these satellites photobombing our images. Yeah, great question.
Any other questions?
All right, and of course, if you have any questions you want to come up with me after the program, that's totally fine too. And the star maps as well. Don't forget to grab one of those on your way out. And of course, enjoy the clear skies tonight. I'm so happy that we have them.
So we have a rule here at Kopernik is you cannot leave until you look through a telescope. And so we ask you to just leave your keys up here, and then you can pick them up after you show proof that you've been through the telescope. One other thing, actually, I forgot to mention. In 2 weeks, so next week's Friday night program will actually be on the Easter Island. The weekend after that, the Friday and Saturday, is our Hocus Pocus haunted observatory. And it's meant for all ages, but we invite people to come up here to get dressed up, and there'll be various activities, some treats for as you go through those activities, and so you can register for that. It's a lot of fun. It fills up, so make sure you, if you're available that either of those nights, to plan to come up. And of course, if it's clear, we'll have our scopes open as well to view that.
And you get tickets right on that web page there. So yeah, that's a really fun event.
So again, we'll definitely have Saturn in one of our scopes. Actually, technically, Saturn and Uranus are right next to each other. Although we are not really going to see Uranus, it's just you really need a much more powerful telescope. If you know where you're looking, exactly. The moon is just now starting to come above the horizon, but it'll take a little bit of time for it to get above the tree line. Doc Carter is here, and he will do a more extensive star tour with his metal cutting laser. Exactly. And so please take advantage of that. I also will remind people, especially if you've been up here, you haven't been up here in a while, when you finally do leave, we just ask you to just be cognizant of where your headlights are. So don't turn your lights on and just keep them aimed in that direction. Just because those lights tend to ruin our night vision. But when you do leave, watch for the deer. They're out. And I actually tend to drive down the middle of the road. It gives me a couple extra milliseconds reaction time. So don't, take your time. One last thing I'll also throw out at you is that you may have noticed on the way up to Kopernik there were planet signs on either side. So again, Kopernik, the astronomer, developed the heliocentric model of our solar system. So when you drive out the parking line, you turn right, you'll see a sign for the sun. 130 feet away is a sign for Mercury. Another 100 feet away is a sign for Venus. 1.8 miles away is Neptune. And those are all placed to scale from the distance from the sun. So you can continue to learn as you're driving home. So thank you very much for coming up tonight.
Thanks, everyone.
Please head on out. And thank you, Jenny.